All right, everybody, for the last couple days we've been practicing antiderivatives, and we've even learned how to use antiderivatives to figure out exact areas. What we're going to look at today is a method for finding antiderivatives of more complicated functions. So let's review some of what we learned about derivatives. When we learned to take derivatives, one of our rules was chain rule. And it worked like this. If you take the derivative of e to the sine of x, you start by taking the derivative of the e to the sine of x part, which is just e to the sine of x. But then you had to multiply by the derivative of the stuff, the chain. The derivative of sine would be cosine. And we called this the chain. Our basic rule for chain rule was you take the derivative of the outside, you leave the inside alone. You take the derivative of the inside and you multiply. Since we are working on finding antiderivatives that we can use to compute areas, we will need a method that undoes chain rule. And we call that method U-Substitution. So here's how U-Substitution works. Let's say I give you this function. If you're looking at this function and you say, okay, I'm going to need the antiderivative, you're going to realize pretty quickly that you don't know any functions whose derivative is exactly this. There is no function out there whose derivative is sine of x e to the cosine x. It's not a rule that we know. So the next step is to realize that if it's not a simple rule that we know, we're going to need a U-substitution to figure it out. What a U-substitution does is it takes a complicated problem, like this one, and it makes it into a problem we know how to solve easily. So step one is going to be to choose what your U should be. Now here's the advice. Your U should be whatever caused the chain. So when I say caused the chain, here's what I mean. We needed chain rule here because this was a sine of x. If it had just been e to the x, we wouldn't have had to worry about it. So the sine being there caused the chain. If I'm looking at this guy, it's pretty clear that e is being raised to something that is not just an x. So having a cosine here would have caused the chain rule to happen. So we let u equal cosine of x. Then we calculate du. Now when I say calculate, I mean you actually have to take a derivative. So the derivative of u with respect to x would be du over dx equals negative sine of x. And then we need to get dx by itself. So here's how we do that. In order to get dx by itself, I'm going to start by multiplying by dx on the other side. So I'm going to have du equals sine of x times dx. Then I'm going to divide by sine of x. So I'm going to have du divided by negative sine of x. For this step, you have to actually solve an equation. Then you're going to substitute. Now here's what I mean by substitute is plug in everything that you have now. So what I usually suggest is that when you get to this point, you put a box around what you have so far, and you keep it on the side. This is sort of like pre-work to do the problem. So we're going to rewrite this integral in a different way. Write the integral symbol, but don't fill in the bounds yet. We're going to do that in a minute. Now, we know here that u is cosine of x. And we know that dx is du divided by negative sine of x. So we're going to replace cosine and dx with what I just circled. So our new function is going to be the sine of x is still there, e to the, instead of cosine, I'm going to put u. And instead of dx, I'm going to put du divided by negative sine of x. So I substituted. Now something should cancel. So in this problem, the sine of x cancels, which means my new simplified integral would be negative e to the u du. Step number 4 is the step that students forget the most often. So we're going to make sure we take it slow and understand how this happens. We need to change the bounds. Okay, that pen is not working. Try again. We need to change the bounds using our u. Now, if you remember, these were both x values. This was the beginning x and this was the end x. But nothing in our problem has x's anymore. So we're going to have new numbers. To figure out our new numbers, which should be u values, we're going to take these x's and we're going to plug them into here to figure out our u. So the bottom number is 0. Cosine of 0 is 1. The top number is pi. Cosine of pi is negative 1. So my new bounds will be 1 and negative 1. Finally, we're going to evaluate our new integral and simplify. Well, it turns out it's much easier to do the antiderivative of negative e to the u than it is to do the antiderivative of this. The antiderivative of negative e to the u is just negative e to the u, evaluated between 1 and negative 1. You would plug in your numbers, so you would have negative e to the negative 1, plus c, minus, you would plug in your other number, so you would have negative e to the 1 plus c, which means when you simplify, you have negative e to the negative 1 plus c plus e to the 1 minus c. So the c's cancel, which means you get negative e to the negative 1 plus e. Let's try this again. So, this whole process is what's called a U-substitution. It takes a difficult problem and it makes it an easy problem so that we can do the antiderivative easier. Step 1, figure out your u. Now in this problem, I'm noticing that in the denominator, I have 2x squared plus 1. And having that in the denominator would have caused me to use a chain rule because I would have needed to do the derivative of the inside of that. So the derivative of 2x squared plus 1 would have caused a chain. So u is going to be 2x squared plus 1. Now du is the next thing I need to figure out. So du over dx is 4x. Then I need to solve and get du by itself. So I'm going to multiply by the dx. And I'm going to divide by the 4x. And all of this is going to be on the side before we substitute. So now we're going to substitute, and we always are going to substitute the u and whatever the dx is. So my new problem will be the integral, and I'm not going to fill in the bounds because I'm going to have to change them, of 4x over, instead of 2x squared plus 1, I'm going to write u squared. And instead of dx, I'm going to write times du divided by 4x. Now right away I'm going to change the bounds, and to do that I'm going to take both of these numbers and plug them into here so I can get my u values. If I plug in negative 1 squared is 1, times 2 is 2, plus 1 is 3. If I plug in positive 2, I get 9. Now something should cancel, so the 4x's cancel. which means my new integral is just the integral from 3 to 9 of 1 over u squared du. Now this is a much simpler problem to do the antiderivative of. 1 over u squared is really u to the negative 2 power. So if I use my rule for powers and I add 1, I get negative 1. Then divide by that and I get negative 1 plus c. Evaluated between 3 and 9. I'm going to plug in the 9 first, so negative 1 times 9 to the negative 1 plus c minus negative 1 times 3 to the negative 1 plus c. So I get negative 1/9, because the 9 moves to the bottom, plus c, plus 1/3 minus c. The c's cancel. Negative 1/9 plus 1/3 would be 2/9. Let's do a few more examples. So the next example, if I'm looking at this function, I can tell it's more complicated than just a simple, straightforward derivative. I can also tell that secant squared is the derivative of tangent. So since this is the derivative of something else that's in the problem, I'm going to make tangent my u, because that way hopefully the secant squared will go away. That must have been the chain. Now the derivative of that would be du over dx equals secant squared of x. And then I would solve that and rearrange it and get du or dx by itself. So du equals secant squared of x dx, which means dx equals du divided by secant squared of x. Okay? So here we go. We're going to substitute. All of this is kind of on the side pre-starting the problem. So I would have the integral from, now I'm going to change my bounds. I'm going to take these numbers and plug them into my tangent function. The tangent of 0 is 0, and the tangent of pi over 3 is the square root of 3. Now instead of tangent, I'm going to fill in u. And instead of dx, I'm going to fill in du over secant squared. So I'm going to have u times, now secant squared is already there. And instead of dx, I'm going to fill in du over secant squared of x. Now something should cancel. The chain should cancel. So my new problem is the integral from 0 to the square root of 3 of u times du. Now the antiderivative of u would be u squared, and then I have to divide by 2 to undo the power, evaluated between 0 and the square root of 3, plus c. Sorry about that. So now I'm going to plug in my root 3. So I would have 1/2 times the square root of 3 squared plus c minus 1/2 times 0 squared plus c, which means since the square root of 3 squared is just 3, I would have 3 over 2 plus c minus, this is 0, so minus the c, which means I just get 3 over 2. We will try some more of these problems in class tomorrow. Thank you so much for watching this video and for taking good notes. And I hope that it makes sense that we can use this process to take a complicated integral that we may not know how to solve and simplify it so that it's easier to do the antiderivative. Thank you again, and I will see you tomorrow for some more practice. Have a great night.